See, I'm still converting my last one. All right, guys. Um, so we're going to go step by step. It's really important that you guys understand um, not just the vocabulary and, about cells and all of that. One of the most important things that you've really, really got to make sure that you understand um, is scientific data. It's really important. And one of the reasons why it's really super important is the fact that on the SOL and other tests that you take, even if, your SATs, whatever, a huge benefit to understanding how to put together a graph, how to create a graph from data and tables, etc., and being able to read and interpret what the graph is telling you. It's when you get questions, oftentimes the answer is right in the graph if you know how to read it. So that's what we're going to talk about. Let me save this. Let me let this person in. Okay, and we'll go back. See what I mean? It's a different one. Here we are. Okay, so I'm going to go over, and if you pay attention, I promise you, it will make sense to you. All right, so first thing, and this is not really week one, but so graphing, lab safety, and then predicting trends in data. Graphing. Whoopsies. Okay, so first we're going to talk about line graphs. We're going to talk about how you create a line graph from data that you have and what they're used for, when they're the most suitable thing to present data, etc. So line graphs are used when one variable, remember your independent variable, is the only thing that's going to be different in every single test group, etc., but are used when one variable affects another, which is the dependent variable. So this is really great when it's very useful for predicting trends, meaning like changes over time, optimal levels of certain things. You're able to, determine when there might have been something that was not usual. It's just very useful. So when we look here, let me move this stupid thing up. Okay. So when we look here, and I'm sorry if it's not the absolute best, I was trying to, I get crazy when I'm doing, especially Google Slides, and then I try to draw a lot of my own stuff, so, I don't get in trouble for copyright or anything like that, but either way. So the number of graduates, So the number of graduates, if we look at this, we can look at, of course, the years, which is going to be my independent variable. And, we're going to see, if there are any trends of the population, I guess, of graduates compared to other years. So we look here, and in 1987, there were only 4 graduates. That sounds like Colonial Beach, my old school. I mean, I don't mean it like that. I'm saying that that sounded terrible, and I did not mean it like that. What I mean is their graduating classes are super, super small, so like 40. But anyway, all right, let's keep going. All right, so 1987, we can look, and we can see that, there was a pretty good increase there between 1987 and 1989. It more than doubled. And then something happened, right? We can go, something must have happened between 1989 and 1990, because look what happens. There's a pretty big dip right there. And it can be anything. It can be anything. Truly anything. It could have been like when Hurricane Katrina, hit, and any kind of a natural disaster can create like a decline in things, right? That have to do with populations and years. So, but this is a way for us to be able to look at this and go, wonder what happened, in these little places right here. We can study those and, determine, if there was something that, obviously was a cause, right? So again, the year that we're looking at, we want to see the number of students each year. And then when we get to 93, and if you look here, something good must have been happening here, because as you see, it just continues to grow. And then something must have happened kind of funky monkey here, right? So anyway, so that is that's one of the most important reasons that we have data, so that we can go back and we can study it. We can look to see if there are any similarities when, there are dips in something or there are increases in something. And it's a really easy way for us to visualize that. All right, so here the federal hourly minimum wage since its inception means the beginning. So, or, when it came about, invented. So we have the minimum age right here. So again, our dependent variable is going to be on the y-axis. Our independent is going to be on the x-axis, right? So we want to see the minimum wage by year. And, you can see here it steadily increases. And then are there any moments where nothing changed at all? These are other types of things that you can see. All right, so the data for this graph are non-numerical. This is bar chart, sorry. So my bar graphs are going to be for data that are not necessarily numerical and discrete for at least one variable. So when you're creating a line graph, you're going to have two variables that are going to be numerical. In a bar graph, that isn't the case. So there are no dependent and independent variables. Axes may be reversed to give a graph with the categories. What did I do here? To be reversed to give a graph with the categories on the x-axis. You know what? You can do this. It depends on the type of information. You really do, even with the bar graph, want to make sure that you continue putting your independent on the x and your dependent on the y. But you might see some, instances where this isn't always the case with a bar graph. So they can be drawn horizontally or vertically. And this type of graph is great for being able to compare things. Uh-oh. Right, so here is an example, of course. What is your conclusion from these results? If we had more time, I would ask you to put that in the chat box. But let's go ahead and look at it real quick. So we have defects, right? And then we have factor A, B, and C. So we want to basically see which one is producing probably the most defects and the least amount of defects. It's just an easy way to compare. And part of the reason why it is so easy is because it's easy to visualize it. You can see when something is taller than something else, right? Or longer than something else or whatever. So this is just a really easy way to take that data that we have and put it together in a graph to represent, what we're trying to represent. But to be able to easily determine, the answer to some questions. So here is one that is a horizontal. And again, it's my preference, but I prefer to do it the other way around. I wanted to show you that you can do it this way. So here we have the number of immigrants, right? And we've actually switched where we have the independent here, we have the dependent here. The reason why I'm showing you this is because it can be done this way. But again, if more than likely, no, not more than likely, pretty much definitely the SOL is going to show you different graphs where you're going to have to identify which one is the independent and which one is the dependent. And I have never, ever seen an instance where they do it this way. Okay. And also we can use my dry mix if you guys remember that. So, and I'll get there in just a second because we are going to look at that a little bit more in detail. But we've got the number of immigrants and then we have the countries, right? France, huge population of immigrants, you know, have come in, but we don't really have a, I thought I had a title on this. I'll have to look at that. There should be a title. Oh yeah, I thought I had that. Okay. So what question is being answered here? And basically that's something that we have to ask ourselves in order to come up with a title. But better yet, we want to have a title so that people know what this actually represents. Okay, fine. The number of immigrants in Brazil. Is there a specific time? You see what I'm saying? So you need to make sure that is one of the other things that you add. As with bar graphs, pie charts are used when the data for one variable are discrete. So these are categories, and the data for the other are in the form of percentages or parts of a whole, so proportions. A circle is divided just like a pie, right? And it's divided into, okay. This is definitely not suitable for data sets with very large numbers of categories for obvious reasons. You know, just like with a pie, you know, you can only cut so many pieces, number one, and who wants a tiny little sliver, right? And you can't make all these little slivers. How are you going to read it? So it really is it's better suited for smaller data sets. Okay. So, let me see here. Okay, so should our schools require students to wear uniforms? Hello. So here's a pie chart. Here's your key right here. And obviously, most students do not want to wear uniforms. And I can understand. I taught at a school that had uniforms, like the polo shirts and the khakis, and they their shoes had to be a certain color. They couldn't be, they couldn't have like more than two colors, I think, on their shoes. It was absolutely insane and ridiculous, and I absolutely hated it, but that's just me. All right, so let's move on. All right, so here's another example of a pie chart when it's appropriate to use a pie chart. Music preference for young adults. What's your conclusion? So yeah, so we can look right here, and we can see clearly, very clearly, that rap is the preferred music genre for young adults. All right. So we are skipping that lesson because we've already done all this and I'm not doing it again. So what time is it? Oh, we still have a few minutes. Cool. Because we're gonna practice a little bit with some graphs. And I wanted to add something. Well, I've got some more details to add. All right, so lab safety and equipment. It's better to be safe than sorry. Always ask your teacher. That's always the answer, by the way. Always wear goggles and aprons. I'm told to do so. Make sure that long hair is tied back. Very, very important. When you're working with, things that are on fire. Bunsen burners, things like that. You don't want to dip it into a chemical. You don't, Goggles, of course, for obvious reasons. Closed-toed shoes, most definitely. Any accident that happens, you should always report it to your teacher immediately. That is always the answer. Always, always. If you can't notify the teacher because of an injury, then have your lab partner or someone else, that is around. That's how you would deal with that. A safety with gases or inhalants. Do not inhale any gas or vapor unless directed to do so by your teacher, which really won't be. But what you want to do is you want to waft it. So let's just say, here's my chemical. I'm not going to be like, or like drink it or whatever, right? So I'm going to waft it, waft it, waft it, waft it. All right. Yeah. And then you always want to use a fume or a vent hood when dealing with materials that emit like gases or vapors. Chemical storage, they must be stored in a clean, dry place. Yes, chemicals should never, ever, ever, that used chemicals should never, ever be put back into the original container. That just eliminates contamination, and you don't want to do that. Always pour acid slowly into water. Do not pour water into acid, please. Use common sense. So when using scalpels and sharp things and the dissection pins, things like that, make sure you're being careful. Make sure that you have a good space to cut objects in. Always cut in the direction away from your body and away from other people. Okay. Use tongs or use insulated thermal gloves or holders when handling heated objects. You definitely do not ever want to go and grab, a beaker off of a hot plate or, a stand with a Bunsen burner under it. You don't want to, grab a test tube, once it's been heated up. So, this is obvious, right? Don't ever point the end of a test tube at yourself or anybody else when heating it. Ever. Okay, the 4 C's: caustic, carcinogen, corrosive, and combustible. So caustic can corrode, destroy living tissue, so skin, and it will burn. A carcinogen is anything that tends to produce cancer. Corrosive is something that will eat away. And then combustible, of course, is capable of like blowing up, catching fire, burning. Okay. Hazard ratings. So, I'm just going to go through this part really quickly. You really don't need this part, but, it's good to know. So rate hazards from 0 to 4. So 0, of course, would be minimal. 4 would be deadly. Red is going to be fire. Yellow, reactivity. Blue, health risk. And white has special info. So lab equipment. Let's look at the lab equipment. What is... Let's see. Okay. When you're measuring liquid, to get the most accurate measurement, you're going to use a graduated cylinder. The graduated cylinder must be read at the bottom of the meniscus. The meniscus is a little dip that occurs in the water, and that is actually due to what we're going to be talking about tomorrow, properties of water. It's due to adhesiveness. So water is very sticky, tends to stick to certain objects, and it does stick to glass and plastic, and therefore it's going to create like a little dip. So you want to read it at the bottom of that dip. There are a couple of different ways to measure volume. You can measure liquid volume by, measuring it in the graduated cylinder. You can also measure volume if it is a regular shape. You can measure it by calculating the length, and the length times the volume times the width. If it's an irregularly shaped object, like, I don't know, anything you can't measure with a ruler, you can use the displacement method, where you take your graduated cylinder, you fill it up to a certain point, you take that measurement down, then you place that irregularly shaped object inside of the graduated cylinder, and then you take down the new amount, write that down, subtract them, and then you will have your volume for that irregularly shaped object. Okay, measuring mass, we can use an electronic or digital balance or a triple beam balance. And we are going to go over those, even though, we don't have them right in front of us, but I can still show you how to do it. Temperature is measured with a thermometer. We can measure pH with litmus paper or a pH meter. Distance, of course, with a ruler or meter stick. I think I have more people in here. Oh, yeah, I do. Yeah, I do. All right. So, again, we come back to conclusions. So, once we've performed our experiment, we have gathered our data. We're analyzing our data to come up with a conclusion. Or predicting a trend, right? So so with test taking, when you're drawing a conclusion or predicting a trend in the data, you have to base your answer on the data given, which is really awesome, right? Because it's right there for you. Which means that the answer is going to be there somewhere, unless, it's like short answer or whatever. But you do not, this is so important, and this is part of the reason why I was explaining that at the beginning, is, this is an easy way to answer questions. So just make sure that you use whatever is given to you. If there's an answer in there that is like nothing to do with the variables that are being presented on that chart, it's not the right answer. Okay, so that's just kind of a little tip. But let's go ahead and we're going to look at one here, and then those of you that are in the block schedule, so just this is your fall block. You guys can go, and then as soon as I'm done with this one right here, and then everybody else who isn't, who's in it for the year long, then you can stay. All right, so according to the data in the table, about how far can a spring be expected to stretch when a force of 3.92 newtons is applied? So we can look at this, right? Let's look at it. Where is it? Hold on. Dang it. So we can look at our forces right here, right? Yeah. And we see that the force only goes up to 2.94, correct? But we can eliminate some things. We can eliminate some things pretty quickly. Obviously, 3.92 newtons is more than 2.94. So what can we automatically get rid of? We can get rid of the 10.5 centimeters. 3.92, so if a couple of other things that we can do is we can go and we can add these together to see, if they end up adding up to one of our known units, or I'm sorry, subtracting. So in this particular case, we're going to add 10.5 plus 3.5. And why are we doing that? Whoopsie, sorry guys. So each time the force goes up, it goes up 0.98. Then the spring is stretched 3.5 centimeters. So you can do the math here because you're given everything. And then you can go back and you can plug in what your answer is and see whether or not that works. All right, the very last one. So the diagram illustrates how some characteristics of the horse have changed over time. Along with the difference in size, what is another anatomical means structure, difference between the modern horse and its ancestors? So they've given you, the type of horse, and then they've given you two anatomical two pieces of anatomy, okay? And you can go and you can compare these, right? So the next best thing for you to do is to go and look at what the answers, I mean, unless, you're just like, yeah, I see it, the answer right then, that's awesome. But you can also go and you can look at the answer options. So here the structure of the tooth has been adapted for eating meat, right? Okay. The size of the molars have decreased. Oops, sorry. Oops. The length of the forefoot has decreased. So you have your forefoot here. This is over time. So these are going to be our oldest. These are going to be our most recent, right? So the length of the foot has decreased. Is that true? Well, no, of course it's not true, because look what's happened. Over time, it's increased, so we know we can get rid of that. But these are just some examples. We'll go over a couple more of these, probably like once a week or so. But anyway, if I have all my year-long people in here right now, awesome. Give me just 1 second to go grab my coffee and we'll get started. While I'm going to go get my coffee, what I would love for you to do is for you to tell me one interesting thing you did this weekend in the comments. I'll be back. Huh? Yeah. Really, really hurt. Just cut a chunk out of my daggum thumb. Okay, let's see. Okay. Awesome. Are you guys here? I only got one. Why is this coffee cold? It's cold. Let me see. What was I doing? Okay. Well, this is crazy. Where's my menu bar?